a mathematician, as a programmer, as a researcher? Yes, anyone. Make a flow chart step by step. Okay, flow chart for the flow of the traffic, or what we can come up with, we can come up with a model, right? A program, so that it's not like that we will be standing in middle of it and then we will regulate the flow, right? As a researcher, we come up with a solution so that it can be implemented, right? We will write some code, and then whatever the theory that we know, based on that we come up with the model, and then we come up with an algorithm, and then we try to solve a particular problem, right, for application. Now this real world problem is there, we try to convert it into a representation first, right? So over here the representation is, let's say, the modeling, we call it as a modeling, or you need to convert it into something that you know. Then from that modeling, we ask some question, we can come up with some inference, some predictions, right? So we will see that how we can come up with a solution. So in the research, specifically, first we define a problem, a machine learning problem, and try to propose a solution. So for that, we try to see that if there is the data available or not, then we design the data for the model. We determine where data come from. We determine where can we get the data easily or not, what are the inputs, right, what are the quantifiable outputs, and like that. Then we construct the based on that, we split the data into training, testing. We also identify the features and label with it. Then we see that can we transfer the data, or we apply the pre-processing method on it, and then we transform the data to explore and clean the data. We go for the feature engineering thing in it. Then any particular model we use, and for example, we can go with the random forest, we can go with the Navier bias, we can go with the decision tree, we can go with the SVM, right, neural network. And then we fed our data to the model, and correspondingly it uses the model to make the prediction. So when we talk about the machine learning, this is the normal flow, all of us know by now, that a data set is there. We first apply some pre-processing method, then feature engineering is then there. We divide the data into training, testing, and then we train the model, and then we evaluate the model. So now today I will be talking about this evaluation of the model, right? So this evaluation, how we evaluate the model. If I am having 3 or 4 or 10 models, then how to compare them? So comparison for the experiment result, right? Research studies may involve the comparison of different algorithms. As we discussed, we can propose different algorithms, methods, or approaches. Now, what exactly we want? We want to compare, depends on what my research problem is, and then correspondingly, we need to formulate my problem statement, right? So that comparison is not always straightforward when our algorithm and their input represent some stochastic behavior. Stochastic means some randomness in it. For example, if I'm dealing with the evolutionary algorithm or ant colony optimization, gray wolf optimization, or genetic algorithm, in that my data is not, the initial points are not the same, right? Always. Even in neural network, the initial value of the weight is also not same, right? So we need to see that how to present our result, right? How we can compare the result. Uh, what happened that if different run may give different result, then how to compare them? What is the meaning of it? For example, if I am using the genetic algorithm, and when I run the program, right, for the first time, it will give a result, right, some output. Correspondingly, that output is O1. Likewise, for the another run O2, for the another run O3, right? Same case, this is for, let's say I am running that particular algorithm for 10 times and then at the end, average of it. Same case for another method. So this is method 2, algorithm 2, or this is method 1. Then the question is how we can compare these results, right? So for that, you must have heard of certain test, parametric test, non-parametric test. We will talk about them today. So in case of the statistical based approaches, right, basically deal with the collecting, analyzing, interpreting, presenting, and organizing of the data. It help in making the informed decision, identifying the pattern and drawing the conclusion from the data. So there are two types, right? One is descriptive statistics and another is the inferential. In case of the descriptive statistics, right, we based on these samples, right, we describe the sample or summarize information about the sample. For example, let's say I am having a student group of 60 in my class. If I need to define how good or bad that particular class is, then one way is that I can talk about their CGPA. I will not talk about average individual CGPA. Instead of that, I will talk about the mean CGPA or mean average CGPA, right? So basically, we are dealing with the central tendency in that. Likewise, we can also come up with the variance and standard deviation in it. We can also represent that particular sample population in term of the percentile or the range, or using the graphs also. In that we use the box plot, a scatter plot, or histogram. The another method, statistical method, is the inferential based. In that, we use a sample data to make prediction or inference about the population, right? So what is the meaning of it? In this, we, let's say, want to come up with a uh, exact poll for a particular election. So I cannot go to each and every particular voter and ask that to whom you, according to you, will win, and like that. So what we did, instead of that, we take a sample from the broader population. And then let's say I have taken a sample of 10,000 people. And then we tried to see that whatever is the result, whether they like A, they prefer A or B. Then we try to see, can I say that whatever is the result of this 10,000 people is a true representation of my overall population. So for that, we go with the different hypothesis testing. In that we have the t-test, z-test, chi-square, ANOVA test, right? Confidential interval also we go with regression analysis, probabilistic distribution. In this, we will talk about the hypothesis testing. Now, there are different factors for choosing a statistical method. It may be the level of the measurement and type of the variable. So based on that, we have the nominal data, ordinal data, interval data, or the ratio levels. Then we have the samples we can divide based on the categories: one sample, two sample, again dependent, independent, paired, right? And third is the purpose. So if my research is descriptive, or I want to find out the relationship or group comparison, correspondingly we need to see that what type of the statistical method I should select. So when we talk about the quantitative research, right, in that descriptive study is there. So let's say over here, this is the error comparison for charge and discharge model. I am thankful to my PhD scholars and some members from the Ramalam. From there, I have taken this particular result. So in that group, when we compare the group, then we have one sample t-test or two group independent t-test or paired t-test, right? And likewise, when we are having more than two groups, then when we can have one way ANOVA, two way ANOVA, repeated measures ANOVA and like that. Now, based on the assumption we take about the data, correspondingly we have two type of the test, right? The first type of the test is known as the parametric test. Another is non-parametric test. So today in this session, I will be talking about dealing specifically with the parametric test. So in this, if the information about the population is completely known, means I know that what is the nature of the population, right? By mean of its parameter, then statistical test is called parametric test. So if I know that what is the distribution, whether it is Gaussian based or T based, right? Distribution is there. Correspondingly, we have Z test, T test, F test, ANOVA, and like that. If I am not assuming any distribution, then we have the non-parametric test. In that one constant test is there, right? Mann-Whitty U test is also there. So this is the broader category of the hypothesis testing. So as I told you, we can divide it into two parts, parametric test and non-parametric test. Again, in parametric test, based on the number of the samples, one sample I am considering or two samples I am considering. So for that, we are having T test and Z test. Depending on the number of the samples, again, if I am having more than 30, we go with Z. If I am having less than that, T test. Independent samples are there or the paired samples are there, then two group test or Z test. We will talk about this. And then in case of the non-parametric test, we have this chi-square. We in one sample, two samples. Again, we have dependent, independent, and the paired sample. In that, we go with the Wilcoxon test or the median test, Mann-Whitty test, chi-squares, and like that. So for our case, at the end, we will be having some result, right? So you can treat the performance of your algorithm as some random variable. Let's say this is the result of A1 approach. This is the result of another A2 approach. And these are the result after, let's say, 20 runs, right? So in statics, each of the cell is referred to an observe. So over here, these are the observation. And each column is called as a group or sample. The performance metrics being monitored in the response over here and the algorithm are the treatments. So we need to see that how to compare the random variable based on the corresponding group of the observations. So for that we have some hypothesis testing, statistical hypothesis testing. So first thing is that what is a hypothesis? Hypothesis is let's say is a particular statement that we consider that okay, based on my particular study, I will try to identify whether this particular medicine has a positive effect or a negative effect, right? So I'm considering that it is a positive effect like that. So it is the assertion or conjunction about the distribution of one or more random variables. And for that, we have some test rules or procedure to decide whether to reject a hypothesis or not. So this hypothesis test is a method of statistical inference used to devise where the data at hand sufficiently support a particular hypothesis, as I was telling you. So there, in hypothesis testing, we are having two type of test hypothesis. One is null test, another is alternate null hypothesis and the alternate hypothesis. So in hypothesis testing allow us to make probabilistic statement about the population parameters. In research, we often want to answer question about the population based on some sample data, as I was telling you. But because of the natural variability, maybe error in the sampling, right? Sample result might not exactly match the population truth, right? So if I'm considering that, okay, my average height of my student in SVNIT is, let's say, 157 centimeter. Now, it's not like that I have reached to each and every particular individual student and then I have measured the height. We will consider some of the samples and then based on that we will try to infer. Now, it is very much possible that I have selected only a special case in the during the testing, right? During when I'm collecting the sample. So we need to cross check it. So we survey 100 people about an average screen time. Their mean is, let's say, 3.5 hour per day. And then we need to see, is this enough evidence to say the true population mean is also 3.5 hour. So we cannot rely, as I told you, on a simple statistical alone, right? So we need a formal procedure to determine whether whether the observed difference are due to the chance or represent the real effect. So based on that the hypothesis, right, we will try to see whether this particular output is a true representation or it is due to some random chance, right? So hypothesis testing provide a structured way to assess the claim about the population parameters. Uh, we will also see that how we can control the error, such as the type 1 and type 2. We will talk about what these are. And then we can come up with some decision. We can make some objective and data-driven approach. Without hypothesis testing, conclusion would be based on the guess rather than the statistical evidence. That's why I was telling you that we need to come up with uh, mm, some support actually using these tests. So as I told you, null hypothesis is a statement that assumes that there is no significant effect or relationship between the variable we study. While in case of the alternate hypothesis, a statement that contradicts the null hypothesis and claim there is a significant effect or relationship between the variable being studied. So null hypothesis, it's act as a starting point for a hypothesis testing and present the status, the assumption of no effect of until it prove otherwise. So we consider that, okay, whatever I'm assuming null hypothesis is true, right? If there are the contradictory to this, then we say that, okay, we go with the alternate hypothesis. So the purpose of the hypothesis testing is to gather the data or evidence to either reject or fail to reject null hypothesis in favor of the alternate hypothesis. So as I told you, we also need to see that how to deal with these errors. So there are two type of error. Type 1 error or type 2 error. Type 1 error is false error and type 2 is false positive and type 2 is false negative. Type 1 error occur when the sample result lead to the rejection of the null hypothesis when it is in fact true. Means my hypothesis was true, but the sample result lead to the rejection of it. So it is the mistake of finding a significant effect or relationship where there is no relationship. So the probability of committing a type 1 is denoted by the alpha. This is also known as the significance level. While in case of the type 2 error, right, it occurs when based on the sample result, the null hypothesis is not rejected when it is in fact false. Right? The researcher fails to detect a significant effect or relationship when one exactly exists. So we consider it as represent it as a beta. So as you can see over here, my hypothesis was true and it was rejected based on the sample. So it is type 1 error, right? If my hypothesis was false, but it was accepted because of the sample that I have collected. So it is type 2 error. Rest these are the correct decisions. Now in this, how we say that it is correct, not correct, for that we have a concept of significance level. It represents the probability of type 1 error. So as you can see over here, this is the distribution. So the assumption over here is that I know the distribution, right? So this is a normal distribution, right? So it is a predefined threshold used in hypothesis testing to determine whether the null hypothesis should be rejected or not. So the data point over here, right? It is the value is more, right? So the confidence is also more over here. The mean value is more, and the points over here, right? These. It represents the probability of rejecting the null hypothesis when it is actually true and is also known as the type 1. So here we say that, okay, my significance level is 5% or point alpha value is 0.05. Right, so we are willing to accept a 5% chance of type 1 error. So we say that, okay, my confidence in the overall output is 95%. But there are certain critical applications for which we need to come up with a lower value. For example, 1% significance level. So we never choose a large alpha just to force the null hypothesis to be rejected. Ideally, we choose alpha before running the test. So small alpha make it harder to reject the null hypothesis. That's why it reduces the type 1 error. But there are chances that type 2 error may increase because of this. So choice of alpha depend on the context. For example, as I told you that in case of the critical or medical studies, we often go with the 1% chance of the type 1 error, or in term of the significance alpha value, it is 0.01 to minimize the false claim. Now, there are different type of the hypothesis test, and we divide them into two part. One is the parametric test and non-parametric test, as I was telling you. And it is based on the parameter we are testing whether population standard deviation is known or not, sample size and assumption about the population distribution is known or not. If they are, the answer is yes for these, then we go with the parametric test. So we make inference about the parameter like mean and variance in that, and it is based on the assumption of a specific distribution. Either it is a normal distribution or it's a t distribution. We will talk what this t distribution if you are not aware about. In case of non-parametric, as we discussed, make inference about the frequency distribution like medium or distribution type, right? So in that we have this z-test. Z-test is named after the z distribution, which is the normal distribution, right? Normal distribution with mean 0 and standard deviation 1. So we use a z-test under these following conditions: test the mean of the population, the underlying population is normally distributed, the population standard deviation is known, and the sample size is large, right? Should be greater than 30 by the central limit theorem. Now, let's say I'm considering one particular example in that a factory claim its light bulb lasts 1200 hours, right? Or in that I am considering the sigma, the confidence as the 100. Standard deviation it is 100. A sample of 36 bulb was taken randomly and it yielded 1160 hours. Now we want to test if the mean life is lower than claimed at alpha with a confidence of 5%, right? So with a 5% of the type 1 error we can tolerate. So we know that one sample Z test, the mean is I'll calculate the Z is X bar minus mu 0, where mu no, 0 or not is hypothesis population under null hypothesis. Then the sigma is the population standard deviation divided by total number of the sample size. We can use these in case of the quality control in the manufacturing, compare the sample mean to population mean in a standard assignment or any situation with larger n and sigma value. So this is the step basically in Z test. We first start with the hypothesis. We consider that as a null hypothesis, let's say. We consider the null hypothesis as the mu naught. So we will see that what mu naught is, and then alternate hypothesis is the reverse of it. So it is not equal to if it is two-tailed, or we can say that my hypothesis is greater than the given one, mu is greater than mu naught, or mu is less than mu naught. It is one tail or two tail. What is the meaning of it? Let us consider one particular example, that if somebody, if the company want to introduce a new chip packet, right? Right now, green packet is there. Let's say another some gray packet they want to introduce. So in that case, they want to see that okay, whether it will affect or not, right? In those cases, we go with these tests. Another case maybe, let's say, in that wafer packet, we consider that the weight is 50 gram. So my 50 gram is basically the null hypothesis. We consider the mu as a 50 gram only. And in case of alternate hypothesis, we consider that other than that 50 is my alternate hypothesis. So if I'm considering this is two tail, in case of one tail, I'm considering that it is less than 50. And another one, I can consider it is more than 50, but not equal to 50. That is my alternate hypothesis. Then we go with the significant level. Then we compare the Z statics, right? Then we find the critical Z value using the Z table based on the alpha and the tail values. Then we make a decision if Z is greater than equal to critical Z, then we reject it, right? If it is less than or equal to critical Z, then we fail to reject the H naught. Or we can also go, this is in case of the region rejection problem. Or if we go with the P-based approach, then we replace this Z value with the P values, right? Then state conclusion based on the given output we interpret in the context of the research questions. So this is the that table you are using. So in that I am having the negative as well as the positive values with me. Now, step involved in the hypothesis testing. Hypothesis testing can be done in two decisions, right? One is based on the rejection region approach, as I was telling you. Another is the p-value approach, right? So let's see what this region rejection approach is. So in the hypothesis, the rejection region refer to the region of the values for the test statics that are considered extremes. So if this is the case, we need to see what will we reject it based on this particular. So we formulate a null hypothesis and an alternative hypothesis, select a significance level, check the assumption, decide which test to apply based on the number of the samples. Then we state the relevant test statics, we conduct a test, and then we reject or accept the null hypothesis. So as I told you that we are having one tailed or one side test as well. So in one side test is used when the researcher is interested in testing the effect in a significant direction, either greater than or less than. So as I was telling you, wafer size is more or I'm saying that the chips in that particular packet is 50, right? So if I go with the two a single tail, so in that my hypothesis may be that if I go with the right tail, it means greater than 50, and if I say less than 50, then I go with the left tail. The advantage is that it is more powerful than the two tail test. In case of the two tail, what happened that I will consider that the researcher is interested in testing the effect in both the directions, right? The alternate hypothesis is a two-sided test or not equal to. I will say that it can be anything other than 50 gram. Okay, so as I was telling you, this one tail is more powerful than the two tail as the entire significance level is allotted to one tail of the distribution, or it detect an effect on the specific direction, right? Assuming the effect exists in that case. So the tests are appropriate when there is a strong hypothesis or a practical reason to test for effect in a specific direction, uh, greater than or lower than, like that. The limitation is that we missed the effects. One test can miss effect in the opposite direction. The test will not be able to detect it, which would lead to the incorrect conclusion. So only I am checking whether it is greater than 50 or not, right? But it may be less than that. Or increased risk of the type 1 error also, right? Because we are searching in the opposite direction than one specified in the alternate hypothesis. In case of the two-sided or two-tail test, uh, we use it when we know when we are interested in testing the effect in both the directions. The null hypothesis is this one, that it is not equal to value, that the weight of the chips, is not equal to 50 gram. The advantage of this two-sided is that detect the defect in both the direction. Earlier, this was the limitation in one-sided test, one-tail test. It makes them suitable for the situation where the direction of the effect is uncertain, or when researchers want to test for any difference between the group of the variables. It is more conservative. The test is more conservative because the significant level, alpha level, is split between the two tails of the distribution now. So this reduces the risk of the type 1 error. But the limitation is it is less powerful, as we discussed earlier. It is not appropriate for the directional hypothesis. This test is not ideal for case where the researcher question or hypothesis is directional. For those cases, we need to go with one tail test on. So let's say this region rejection approach, I considered one particular problem. Suppose a company is evaluating the impact of the new training program on the productivity of its employee. The company has data on a average productivity of its employee before implementing the training program. So what I want to see, that what is the effect of the training, right? So in that, what we can say, let's say, what is the effect of a particular medicine, right? So the average productivity was 50 unit per day when with a known population was 50 unit per day with a known population standard deviation of 5 unit. So we consider the value mu as 50. So this particular tell me that it is 50. Now, after implementation the training program, the company measured the productivity of a random sample of 30 employees, right? The sample has an average productivity of 53 unit per day. So now you can see, should we go with the one tail or two tail over here? Just tell me, we should go with the one tail or two tail? The company want to know if the new training program has significantly increased productivity or not. So we do have research problems. Yes, one tail. So we do have research problem in that we want to consider that what is the effect of a particular exercise, what is the effect of a particular medicine, right? So we consider for this particular example of the training, we consider the mu as 50, and because we want to see that productivity increases to 53, so greater than before. So it is a one tail problem. And significance factor we consider as a 5. Why? Because the standard deviation is 5 unit, let's say over here. We represent. So assumption is normality valid, population standard deviation is known. So we can apply the Z test over here, right? So we know the updated value, average productivity now is 53. The previously it was 50. The significance, the standard deviation was 5 in it, and number of the sample is 30, right? So we come up with the value of Z as 3.28. Now we need to check the Z table, and Z table shows the area of the left region only. So you can see over here. So this Z table, we try to see where that particular value is. So it came out to be as 3.28, right? So we see that, okay, this 3.28 represent so area 0.95 was found at the value of 1.65, because we want to see the significance. It is not directly mentioned, so we see that, okay, where is that 0.95, because that is my significance level. So it came out to be the value as 1.65. We do reverse engineering over here. So 1.65, right, is over here, while the Z value is 3.28. It is very far from the region rejection from 1.63. That's why we had a strong evidence against the null hypothesis in favor and it is in the favor of alternate hypothesis. And because of this, we can reject the null hypothesis. Now, let me consider another problem. Suppose a snack food company claim that their Lay's wafer packet contain an average weight, as I was telling you earlier, of 50 gram per packet, right? So, my hypothesis, null hypothesis is that every particular packet is having 50 gram. So, my alternate hypothesis is not equal to 50 gram, right? So, it can be two-tailed now, over here and that side. And again, my significance level is 5% over here. So we consider the alpha value as 0.05 and for both cases it will be divided. So it is 0.25. Right. Again, I am considering the same assumption of normality and the population standard deviation. So we apply the Z test. The Z value came out to be minus 1.58. And when we compare, we checked or look at the Z table, so the area came out to be 0.95, right? 0.95 was around 1.96, 1.96 over here. And 1.96, 1.96, it is for the positive one, it is for the negative one, while I come up with the minus 1.58 over here. So we have got not strong evidence against the null hypothesis, and because of that, we fail to reject the null hypothesis. Right. So my null hypothesis was that the sample has an average weight of 49. So this is the case of the region rejection. The issue over here is that even though the value is 3.28, right, or even the value is 10, I'm not able to give some confidence to that particular. For me, if it is more than 1.65, I will reject it, right? So the drawback of the regional reject approach is that if Z1 is 2.1 and the critical Z is 1.96, you reject H0. Right? If even this Z reaches to 10, we also reject H0. Both decisions are there to reject H0. But clearly the second result is much stronger evidence. So we need to see that how this critical value method does not distinguish between the barely significant and highly significant. So we need to see that, okay, it is highly significant or barely significant. What is the confidence in our overall decision? So a p-value is used. So p-value approach is used. The probability of obtaining a test statistics as extreme as the observed value, assuming the null hypothesis. It measures the evidence against H0. A smaller p-value means a strong evidence against H0. So over here, the p-value is between 0 to 1. P-value is not the probability that H0 is true. If p-value is not the probability that H0 is true, if the conditional probability assume H0 is true. So if we want to go for the p-value approach, the first is again we state the hypothesis, null hypothesis, alternate hypothesis. We choose the significance level alpha. We compute the test statics, right? We need to see whether we should go with the t test or z test. Z generally we go when the sample size is more than 30, right? Compare if the p-value is less than equal to alpha. If p-value is greater than alpha, fail to reject H0. Step 6, state conclusion, is the interpret in context of the research question. So if p-value is less than or equal to alpha, we reject the H0. If p-value is greater than alpha, then we fail to reject the H0. It means we have to accept it. And common significance is same as this. So common the interpreted right, as I told you that p-value is 0.03, significance is 0.05. We will reject it if it is this, and we are not able to reject it. So let's take one more example. If there is sufficient statistical evidence that at 5% significance level to conclude the true population mean exceed 50 based on the sample of 36 observation with a mean of 52 and population standard deviation of 4. So over here we consider again the null hypothesis as 50, alternate hypothesis is greater than 50. It's a one tail, as you can see, it increases, right? So then we apply the Z test, let's say over here. The Z value came out to be 3. Then we try to see, calculate the value of the P value. Most Z table show the area to the left of a Z score. So first we find the area to the left of the Z score for the 3 case. So if we see the Z table, the area came out to be at 0.0098, right? Now what we can say, because we are interested in the right part of it, so we subtract the value 1 minus pz. So it came out to be, the value came out to be at 0.03. Now 0.0013. Now it is less than the alpha, that is 0.05. So we reject the null hypothesis. So we say that there is a significant evidence that mu 50 at 5% significance level. Right, same case for one tail using the P test. So the company claimed the battery lasts an average of 100 hours. A sample of 36 batteries has uh, mean of 96, right? While they are claiming as 100. Test in that significance level we consider as 0.05. But if it is a case of a medical, it will be 0.01, depending on the problem statement you need to select in advance, right? So again, we come up with a hypothesis. We say that, okay, this is a one tail test over here. And because it is less than the one, so it is the left test. Left tail. So we compute the Z again, we identify the value of the Z in it, and then we identify whether it falls in the rejection region or not, and like that. If you want to go for the p-value, the same previous step that we discussed over here may be used, right? You can cross check. So again, this is another example. Let me directly go to the t-test now. T-test is a statistical test used in the hypothesis testing to compare the mean of the two sample or to compare a sample mean to a known population mean, right? The distribution, as you can see, this one is the normal distribution. T distribution in that it is more wider and has heavier tail, as you can see over here, than the normal distribution. So a sample size increase, the t-test approach the Z test. As you can see, if the sample size increase, it will go up, right? And it will be toward the normal distribution. So in that case, we can go with the Z distribution, Z test. So t-test we can use if I know the standard deviation, if the data come from a normal or approximately a normal population with t distribution, if the sample size is less than 30. Now there are three types of the t-test: one sample test, independent t-test, and pair t-test. So one sample test is that based on this sample, I want to identify, okay, whatever is the result of this particular sample, it is the true representation of the population. So we tried, my hypothesis is there a difference between the group and the population output? The another one is the independent two sample t-test. So in that case, the independent two sample t-test is used to compare the mean of the two independent sample. The null hypothesis state that there is no significant difference between the mean of the two sample, while the alternate hypothesis state there is a significant difference. So what we can consider that is there difference between the two group. For example, I consider a case, right? In that we identify that, okay, what is the effect of it, right, on the male and on the female of a particular medicine. So that is independent sample t-test. And paired sample t-test is there a difference in the group between the 2 point in time? For example, I consider a diabetic foot ulcer population, right? And in that, I gave some medicine, some physiotherapy, or some particular treatment to them, and then we identify that okay, what was the status at 0th day and what is the status at 90th day. So for that case, we go with the pair sample. So in case of the sample, single sample t-test, we assume, right, the normality is there, population from which the sample is drawn is normal distributed, independence is there, the observation in the sample must be independent. The random sampling, maybe the sample must be random and representative subset of the population, unknown population and standard deviation is there. In case of independent two sample t-test, it is also known as unpaired t-test. It is a statistical method used to compare the mean of two independent group to determine if there is a significant difference between them or not. Again, we consider the normality, equivariance, random sampling, and independence of the observations. Now, pair two sample t-test, in that we go with the before and after studies, right? Matched or correlated groups. So in case of the medical related problem, if you are working on, then and you want to analyze the effect of the treatment, then you can go with the sample t-test, pair two sample t-test. So again, the assumption over here is that two tests of the observation must be related or paired in some way before or after. Normality should be there uh, in the observation. We can go with the QQ plot or histogram, then we can see that independence of the pair also. Now, when we want to apply these particular tests, right, we have some tools with us, statistical tools. Generally, we can go with the R or MATLAB or SPSS, or even in Python also you can use it. And if you want to use some online tool are also available, so you can go through this link as well. Now, the question is how to select these tests. These different static hypothesis tests are different tests which make different assumption about the population. So depending on the parametric and non-parametric, so if independent is there, then I go with the unpaired t-test. If they are related to each other, then we go with the paired t-test. If the size more than two groups are there, then we go with the ANOVA test. Same case for the parametric, non-parametric, we have the Wilcoxon test or Feldman test or Kruskal test. So let's say these are the result of my machine learning model, right? Machine learning model 1, 2, 3, and 4. So we can compare A1 and A2 and A3, or we can compare A1 and A2 and A3 and A4, or we can compare with all, right? Or I can go with the pairwise comparison of also of n group A1, A2, A1 or A3, right? Compare between A1 and A3, A2 and A3, A2 and likewise. Right, we can compare with the n groups also. Potential way to compare A1, A2. So we come up with the different comparisons. So there we can use these tests. At SVNID, we do have a group of, yesterday I also discussed computational intelligent and smart motion research, right? So we work with the different aspect of the motion analytics, and in that we try to see that the result that we are getting can we give some confidence to that. So for that, let's say we work on the motion rehabilitation. In that, based on the working, as I was telling you, right, we come up with the angles over here, right? In the meantime, you can see that this when this hand come in front of this marker, because of that I'm not able to get the correct output. So we apply some regression methods to come up with the true representation, and then based on the uh, biomechanical approaches, we come up with the angles also, right? So based on that, we are also trying to come up with rehabilitation based system. We also work with the motion robotic hand with we have 3D printers in that we, this we printed at our particular lab only, and based on the vision we are able to control it as well. We also work on the different projects of the robotics, brain computer interface, and other. So we also apply these tests on one of the problem. So for that, I am considering this optimized clustering technique for gait profiling in children with cerebral palsy. So as I was telling you, human gait is way of locomotion. So average adult takes around 5,000 to 8,000 steps a day. This is a minimum you should walk, right? Number of the steps. In that, we have a concept of the stride, stance, cadence, step, double limb support, single limb support, and like that. And we do have a lot of applications in it, as you can see over here as well. We can use it for the medical purpose, we can use it for the rehabilitation purpose, robotic, biometric, sports, right, older care, right? As you can see, we have applied this on gait analysis on the cerebral palsy student as well. And these are different applications, right? So we develop a approach based on the clustering, in that we come up with a data set. It was a publicly available data set, and then we apply different clustering approaches on it, and then we try to see that whether it is able to identify correctly or not. So the data set was of 88 patients diagnosed with the cerebral palsy, and 68 with the normal data set. So in that, we are having the stride, cadence, lag length, and average age. Right. We plot the data first, then we apply the polynomial normalization, right? Then we try to see whether we can come up with a single line to divide that into two parts. We consider three cases in five cases here. Case one, case two, case three, case four. So case one is the stride length, cadence, lag length, and age is the parameter, and we don't apply any normalization and scaling. In case of the case three, we apply the polynomial normalization and scale also. 4 and 5, stride length and cadence length, different cluster size between 2 to 7. So we apply the k-mean clustering overhead, and the issue with the traditional k-mean is that it depend on the first particular point of selection of the cluster head. So to select that cluster head, we have applied these evolutionary algorithms, and that PSO, genetic algorithm, and Gray-Wolf algorithm we applied. We also go with the fuzzy C mean clustering algorithm in it, right? So these are some of the results for case one, case two, case three, with the evaluation parameter as cluster priority index and intra-cluster, MSE, Siloid coefficient Dune index. We apply the t-test on this case 3, as you can see over here, and we come up with a two-tail t-test, right? And the significance level was 5% in it, and the negative t-test value with PSU over PSO, particle swarm optimization, it was giving good result as compared to the other algorithm. So this proved that, okay, statistically, that using t-test, that PSO is performing well as compared to other for case 3. These are some of the results based on which we can identify what should be the number of the appropriate clusters in a particular group. So we considered these three case test subjects, A and B, before surgery and after the surgery. As you can see over here, this is for the normal case, this is prior to the surgery, after the surgery, same case for D2 and D3. And we have identified that we are able to come up with the correct output over here, as you can see. But there was certain limitation in the subject number A. Why? Because in that we are having only the normal conditions, and as well as the age group was also higher as compared to the average one. So here 13 to 19, while uh, as you can see, the mean average with the cerebral palsy was 9 only, and because of that, it is not coming up with the correct answer. That is expected as well, right? As you can see, this is again try to identify that what is the effect of the surgery over here. So with this, I end my session. We are open for the collaboration at CISMR. We are looking for the PhD student or intern if you are interested. You can drop a email to me, or you can connect with me via mobile also, or just drop me a message. We can discuss as well. So if you have any doubt, please ask me. I'm open for the questions. Hello.
One question is in the chat box.
What is that?
Uh,
I'm not
uh,
able to see.
Vijay
Okay. How do the statistical test? If the difference between the model performance is significant? Based on that, you need to come up with a hypothesis, right? I am considering that my PSO is better than all other. So this is my, you can say, hypothesis, null hypothesis. And using these tests, we can prove what is prove that. So whatever you want to prove, consider that as your hypothesis. Because we want to overcome any particular case where we are reducing the chance of getting good result based on some luck. Yeah, any other question? Yeah, I think there's no more question.
Yes, sir. Uh, so thank you, sir. Thank you, Dr. Chandraprakash, sir, for this wonderful session.
Thank you, sir.
Now, this is
Thank
the
you for the
first
invitation.
morning session, first 1 hour that is completed.